What's up, math scholars and math haters? This is Mr. W. Today we are going to start binomial probability. Now this is one of the other big probability ideas that discrete math contains. So today this video is just going to be about learning about and using the big, unwieldy, strange formula that binomial probability makes us use. And I'll start by just going over a binomial probability situation. First, in a binomial probability situation, you have some trial that you're repeating multiple times. Some examples of this could be rolling a die or flipping a coin or something like that. Every trial, every time you do this, you're going to have the same chance of success or failure. This is very, very important because the entire formula for binomial probability depends on your probability being consistent every time you do your experiment or you do your trials. And finally, you're looking for some specific number of successes and failures. You could be looking for a range of numbers, like if you have 4 trials and you're looking to get at least one right, or at least one success. Now that's a range of possible numbers of successes, but unfortunately the way to get there is a little more difficult and tedious. But every time we do one binomial probability experiment or calculation, we're looking for one specific number of successes and failures. And I'm actually going to bring out some colored markers now and go over some of the letters that we'll need to use for this. So first, if you repeat a trial multiple times, whatever number of times you're doing that, you're going to call that n. If your trials have the same chance every time of success or failure, I'm going to give these two names. I'm going to call failure F. That's the probability of failure that I'm calling F. Actually, how about I call it P of F? And then here, the probability of success, I would call PS, probability of success. And finally, the specific number of successes and failures that we're looking for, I will go ahead and call this S for successes and F for failures. I am extremely creative. But now I'm going to scoot this up and you're going to see the shell of a formula and I'm going to fill it in. We're going to use this every time we do an example of binomial probability. So here it is. And as I fill these in, I think you'll start to see some patterns that I'll go ahead and highlight before we get to our first examples. So for instance, this big C. What we're looking for is n choose, if you remember that from combinations, n choose S. This part of the formula is essentially the number of ways that we can do something this many times and get this many successes. And this is times, and inside this first set of parentheses, I'm going to have my probability of success raised to the power of how many successes I want. And then here, I'm going to have my probability of failure. And that P of F is going to be raised to, you guessed it, the number of failures that I want for that particular example or that particular problem. So how exactly does this formula work in an example? Well, let me go ahead and bring one of those up. So here's our first example. We have 4 trials and a 60% chance of success for each trial. And I'm going to go ahead and do this for 0, 1, 2, 3, and 4 successes. All right, so first let's go ahead and establish some of the numbers that we already know. We know that 4 trials is going to be our n. We know that 60% or 0.6 probability of success equals 0.6, which means that the probability of a failure, PF, is 0.4. So these are the 3 numbers we already know for every problem, but what's going to change is the number of successes that we want every time we try this. So for instance, the chance of 0 successes. What this means is that I need to go ahead and fill in a quick bit of information. Successes is 0. And then for failures, if I'm doing something 4 times and I never succeed, how many times have I failed? I've failed 4 times. So 0 successes, 4 failures. I will go ahead and make my formula shell here so we can fill some of this in. And now we just need to fill in all the information. This is 4, choose 0. It's being multiplied by, and I have my success spot. So the probability of a success is 0.6, and that is being raised to the 0 power, and that's being multiplied by the probability of a failure, which is 0.4, and that is being raised to the power of the number of failures, which is 4. And at this point, I can go ahead and type this into my calculator. Now, the calculator can be a little tricky with this formula, so I'm going to go ahead and demonstrate exactly how I do this. To start with, I'm going to put everything in parentheses. So my 4, choose 0, that's going to go in parentheses. And now, my 0.6 raised to the 0, the calculator is going to read this exponential expression like we want it to without parentheses, thankfully. So I just need to go ahead and multiply by 0.4 raised to the 4th power. So here we have all 3 parts of the formula. We have 4 choose 0. We have 0.6 to the 0 power for the number of successes. And then we have 0.4 to the 4th power for the failures, and that gives me 0.0256. So I'll go ahead and write that. There's my formula shell for each of those. And I can actually go ahead and fill in some of the numbers that aren't changing. The trials are always 4. This is always going to be 4 choose something. The probability of success and the probability of failure are not going to change either. So this will be 0.6, 0.6, 0.6, 0.6 the whole way down. And then this one, 0.4, 0.4, 0.4, 0.4. What is changing, however, are my exponents that represent my numbers of successes and failures. So for instance, if I'm trying to find the chance of 1 success, this is 4 choose 1 times 0.6 raised to the 1st power. And then if I'm doing something 4 times and I'm succeeding once, I'm failing 3 times. And then for the chance of 2 successes, this is 4 choose 2 times 0.6 to the 2nd, and then times 0.4 to the 2nd. 3 successes would be 4 choose 3. The probability of success is raised to the 3rd power, and the probability of failure is raised to the 1st power. And finally, if I want to succeed every time, that's 4 successes, 0 failures. Now, I want to point something out very quickly before I calculate the rest of these, and that is that our 2 exponents always add up to the number of trials, and our 2 probabilities always add up to 1. That's a good way to just check your math and check what you've written down. Make sure that your exponents add up to the number of trials, the number of times you're repeating your experiment, whatever it is, and then the probabilities, the 2 numbers inside parentheses, always need to add up to just 1. So let's go ahead and figure out the rest of these. For this one, that would be parentheses 4 choose 1 times 0.6 raised to the 1st power times 0.4 raised to the 3rd power, and that's 0.1536. And then for the next one, 4 choose 2 times 0.6 to the 2nd times 0.4 to the 2nd, and close your parentheses every time or else this is going to get a little crazy. 0.3456, I have room for one more. And now for 3 successes, this is 4 choose 3 times 0.6 to the 3rd power times 0.4 to the 1st power, 0.3456 again. So I'm going to go ahead and write these down as I've got them. And so for that last one, this is 4 choose 4 times 0.6 to the 4th times 4 to the 0.1296. That looks right. So we've gone ahead and used this formula a few different times to figure out in this example where we're doing the same thing 4 times, and there's a 60% chance of success for each trial. The chance of not succeeding, never succeeding at all, is about 2.5%. There's about a 15% chance that we succeed once, about a 35% chance that we succeed twice, about a 35% chance that we succeed 3 times, and then almost exactly a 13% chance that we succeed 4 times. Now I want to do one more thing, and that is to just add all these up, because if I did all of these correctly, we should get a total Our total should be 1. That's exactly what we're looking for, because 1 is the probability number that essentially says everything that can happen. And if we have gone ahead and done a whole bunch of these with the same trials and the same success for each trial, we should be able to add all these up and get 1, because these represent everything that can happen in this situation.